thank you everybody for joining. Once again, welcome to the lecture number 11 of the deep learning course. In this session, we are going to see the backpropagation. That is one of the very important algorithm in the development of neural network based system. And when with the backpropagation only, the all the things that we are actually able to see into the neural network domain. We are actually able to train. So the background that that earlier we were talking about something called perceptron, and after the perceptron, we have seen that perceptron has an issue that when you were training on the bigger databases, the error because the nature of this particular function is such that it only can represent a leader decision boundary. So what was happening, that error was actually fluctuating. So we have actually thought that instead of this fluctuating thing, why not we change, why not we remove the thresholding part from the outer part of the perceptron. But we have actually also later realized that if we are going to do that, error is definitely going to decrease with every learning iteration. But what is going to happen over there, that even if you are going to create a bigger circuit of the neural network, it actually decomposes to only single neural network circuit, so it becomes very bad. So then we have thought that instead of using this activation one, we can use some kind of function which are actually differentiable, and that also give the value into our specified range. So we have actually seen that the one such function that could be that you use sigmoid instead of W transpose X. You know that because W is the weight when it is going to be inside, and X is something that is going to be the input. But at the time when I'm telling that I'm going to remove this activation, I'm going to put some other function that is called the sigmoid function. We have also discussed that there is an important property of the sigmoid function, that if you want to find out the derivative at this point, you can say that sigmoid 1 minus sigmoid. So this is going to be the derivative at that particular point. So therefore training, if you want to do a training, it also becomes very easy. So about this particular change, what is important thing is this, that earlier when we were talking about this kind of circuit as a perceptron, now this particular circuit would be called neuron. Okay, and that's why we actually we are going to use the, when in the later point of time, whenever we are going to make the circuit, we are going to use the neuron only. We have discussed this briefly, that when we are going to have these kind of circuits, we are going to deploy the gradient descent based mechanisms to find out the optimal value of the parameter. Error that we have seen in the last class can be defined into this particular formula, and we have our understanding is this, that we are keeping the things into the layer, and at the last layer there are k outputs. Okay, if there are k outputs, so for any given inputs, we want to see that how bad all these individually all these outputs are. So there comes a summation term for all the things, that how bad we are, and then for all the data item, actually we all the data item we feed over here and try to see that what is the how much deviating we are from the standard behavior, and by this we can define that what is the error. So this is the formula. Any problem in this? Hope this is clear to you, that this formula is very simplified and elegant formula. There is no problem in this. So if you have any issue, please let me know. So this is the error function, and in the last class itself, I have actually told you that general methodology is this, that if you know that there is an error function, and if you want to update the weights, so you say that what is the current weight minus some parameter multiplied by you find out what is the derivative of this particular function with respect to the wi that is there. So this is the standard method that many of the time we are actually doing into our class, that we want to update the value using this thing. Okay, and this error function, as I have talked about, that is defined into the previous slide, that it is defined into this particular way. So how the back propagation is going to do the same thing, it actually try to find out that if you are going to change something, you are going to change something into the weight, how this particular complete error is going to change, and by this you are going to modify the weights, and then ultimately you are going to do the optimization, and your value is going to be minimum. But we have actually seen that actually things are not simple when you have a neural network. So actually it comes out to be that if you want to find out the weight update at this particular place, means just the output layer. So for every data point, you have to update using this formula. I'm not going right now into the detail. We are going to see the derivative of this particular quantity, and very soon. And if you want to find out that how you want to modify this particular weights which are here, so for that you are going to use this particular formula. Okay, these are the two different formulas. And if you want to find out what is the value over here, again you can utilize the same formula, the second formula itself. And this is because the formula requires outputs, and outputs is a set where the things which are going to receive the output that is being produced by a particular neuron. So in this way you find out that what is the value of delta k, and what is into the delta h, and then ultimately when you find out that how much you have to change, you add this into your original equation. And this particular thing, to find out this particular thing, as I told you earlier, that every time we are talking about that, you have to multiply with the eta and xji, that is with respect to the input. So in this way you actually modify the things, and you get the right parameter over there. I know that it is very difficult to go into this particular formulation, that how these things are coming. We are very soon going to see the difference. So let us start and understanding the mathematical part of this particular equation. So everybody is okay with this particular formula. Everybody is okay with this particular formula. So let us just focus on a single input, that whenever you are going to provide some input to your neural network, at that time let me just focus on that. So if only one input is there, so you can neglect this particular part. Okay, if you are just focusing for a single data item, how we are going to update the weights, so this part you can neglect. Yes or no? Can you write yes or no? In this equation we can neglect this particular part, because only one, if we consider only this one data point, we can neglect this particular part. So the equation becomes this, that summation of all this quantity using half of this particular quantity. Same formula we have written over here. And if we want to update, forget about all these things. Okay, if you want to update that, what is the how much I have to change. So again, multiple number of time I'm telling that you find out that what is the derivative of this particular quantity, and with respect to that particular weight, and then this much you have to change. So ultimately you want to find out that what is the value of w. So you can say that w is equal to w plus delta wgi, because minus is already been written over here. This slide we have also seen in the last class, that if you have a neural network, and in this kind of neural network, here how many layers are there? Can anybody tell how many layers are there?
2.
No, there are 3 layers. Okay, so this is the input, this is the output layer, and this is the hidden 1 and hidden 2 layer. So most of the time when we actually talk about the layers, it actually correspond to the places where there are weights. So how many places there are weights? 3 places. Input is actually not considered as a layer, because you are only providing something, but after that, with every kind of layer that you are going to add, you are going to have the dense connection kind of thing. So how many layers here are? Once again, how many layers here are? 3. In the last class, we have also talked about this, that where all the units are given a number 1, 2, 3, 4, 5, 6. And the same way, if you want to find out that what is the connection, every connection has a number. So if I want to find out with respect to this particular unit, that what is the formula, what is the output is being given by this particular unit. So this is the connection, this is the connection, this is the connection, this is the connection. All these connections have their name. This is the first one, second one, third one, fourth one, and we say it x91 x9 because it is with respect to the 9. Okay, once again, x91 x92 x93 x94 is the input that is going to come, and the corresponding weights are w91 w9 w92 w93 and w94, and x1 are x91 x92 x93 x94. You turn by turn do a multiplication and find out the summation, and this is going to be called output given by this O9. Make sense? So what is xij? Once again, what is xij? That is the ith input to the jth unit. So if the unit is 9, this is the fourth unit. For example, 9 4 is means to the unit 9 input, that is the fourth input is this one. So it is highlighted into this particular diagram. On the same way, what is the weight associated? The same weight is also going to be associated in the same way. I have done a mistake. So there is a net j. There is a something called net j. In the last class we have seen what is the net. Net means the multiplication of all these streams. So I have done a mistake. I'm very sorry for that. This is actually net 9. Net 9. What is the net value over there? What is the output? Actually, output is when you apply on this net 9, if when you apply the sigmoid, at that time you get the output. And sigmoid, you know, that is a function 1 plus e to the power minus x. Okay, sigmoid of x is going to be this particular function. So what is the oj? Oj is the output given by this thing. So output of 9, you have seen that. If you want to find out output of 9, it is going to be given by this particular formula. Hope it is clear to you. With every output, you expect that what should be the right output, that is the target one. Outputs is a special set that tells that who are the things into the output layer. So they are the 12 and 13 downstream of j. So it tells that who is immediately receiving the output of that particular unit. So if I want to ask that for whom I can find out the downstream, so I can say that downstream of 9 right now. I am talking about 9 now. What is the downstream of 9? Again, it is going to be these things. Downstream of 6 is, if I ask that what is the downstream of 6, it is going to be 8, 9, 10, 11. 8, 9, 10, and 11. In this way, you create this particular formula. All right. So this is some kind of notation that we are going to follow for a few minutes. Okay. Any problem in this notation? Yes or no? Any problem in this notation? I think we have discussed this in the last class. Yes or no? Any problem? No problem? Mohit? Any problem? No problem? Okay. So we ultimately, we are interested in what quantity? We are interested in ED upon WJI. Can anybody tell why? Why we are interested in this particular quantity?
To update the weight.
To update the weights, because if we want to, because for every weight actually we want to find out. So for every WJI we are interested into finding out this particular quantity. Makes sense? Yes, thank you. So since you know that directly ed is not directly dependent upon ji, so we can expand it using some kind of chain rule, and we can say that ed upon net j and net j upon wji. Here you can say that net j is actually dependent upon wji. How? Because net of j is going to be wj1 xj1 plus wj2 xj2 dot wji xji dot. This is going to be the net j. This is the equation of net j. If you do a derivation with respect to wij, so what is going to happen? So all the things except this particular thing, they are going to vanish. They are going to be zero, because you are going to find out the derivative. And here also, since it is only a single term, what remains? Xji remains. So this particular term becomes what? Xji. Everybody okay with that? Yes or no? This is xgi. This particular term is xgi. Now I want to find out that what is this particular value to find out this particular quantity. So let us focus on this particular thing into more detail. So one by one I am going to find out this, and the equation for this particular quantity is different from when it is a you know that when right now let us just focus on two things. That let's assume that this is the input layer, then there is a first layer, then there is a second layer, and then this is the output layer. Okay, output layer. So how many layers there are? One layer, and second two layer. So first we are going to see that what is this particular quantity with respect to the output layer, and then we are going to see that what is this with respect to the hidden layer. And this thing again, we can, if there are multiple layer, the same mechanism that we are going to use here, we can extend it to find out the values if there are even multiple number of layers. So right now we are going to see the value, the ed upon net j with respect to the only output unit. Once again, for the output units, if we want to find out that what is the value of ed upon net j. Okay, again since you know that output is not directly dependent, ed is not, may not be directly dependent upon the single net j. So because multiple things are there, so I can apply some kind of again chain rule. I can say that ed upon ed upon del ed upon del oj multiplied by del oj upon net j. Can I write like this? Again, it is going to be what? Chain rule only. So there are two different parts. So one by one we are going to see this. So let us focus on the first part only, this part. So this part is this ed upon oj. Okay, so what is the formula of ed? You know that the formula of ed is this half of this particular quantity. Any problem in this? This is what the formula is. So multiple outputs are there. So this formula, because k different outputs are there, it is going to be t1 minus o1 square plus t2 minus o2 square plus dot 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 tj minus oj square plus dot dot dot, multiple things would be there. And since you are finding out the derivative with respect to oj only, so only this term is going to survive. All other things are again going to be zero. And if they become zero, and then you can directly apply the derivative inside. So if you are going to find out the derivative with respect to oj of this particular quantity, what it is going to be, 2 multiplied by tj minus oj del upon del oj of minus oj. Okay, and this gives you what? This gives you minus 1. So you get this particular quantity. Am I right? You get this particular quantity because there was a one half written over there intentionally. So this actually cancel this particular part, and ultimately what you get minus of tj minus oj. Any problem in this? Yes or no?
No, sir.
Any make sense? Okay, so let us see the second part. It is oj minus del oj upon del net j. So you know that oj, what is oj? Oj is the activation function when you apply on the net j. This is only this thing. So ultimately what you want to find out, del upon del net j divided by del net j. So if you can see that's many of the time you have seen into when you were into the class 12, that if the same thing is here and there, then sometime you can replace it with any other value, and you can do the replacement and find out that you can solve the derivative in this way. You can say that del upon del x upon del x, you can find out similar kind of thing, and after when you get the answer at the x, you you replace the net j into this particular value. Make sense? Yes or no? So using the same thing, if this is right, then let us first try to see that what is the value of derivative of sigmoid with respect to the x. And you know that sigmoid formula is 1 upon 1 plus e to the power minus x. You know that 1 plus e to the power minus x to the power minus 1. So it becomes minus 1 plus e to the power minus x to the power minus 2 del upon del x. What? Am I right? Del upon del x upon the inside term over there, and derivative of this becomes 0, and e to the power minus x becomes minus of e to the power x. Am I right? Yes or no?
Yes, sir.
If it is like this, then e to the power minus x, you add 1 to it and subtract 1 to that. So it becomes minus e to the power minus x. So you can say that this plus this, and this minus 2, you can say that 1 plus e to the power minus x to the power minus 2, and then 1 comes here, 1 plus e to the power minus x. So you can put like this, and you can, if this rearrangement makes what does for you, that this particular part is sigmoid of x, because again the same formula. And into the second part, what happens, that this goes inside and tells this particular thing is same. So 1 upon 1 plus e to the power minus x minus 1, it becomes like this. So sigmoid of x, and let me go there. I think okay. I think I have missed just one point, that there was a minus 1. So you multiply over here. So this becomes positive, plus 1 minus 1, as I told you that you can add, and ultimately you come up to this particular formula, sigmoid x into sigmoid of x into 1 minus sigmoid of x. Is it fine? Many of you may have learned this formula while you were preparing for your IIT JEE. So this is the same formula that we are going to utilize. And since few minutes back we had talked about that this derivative need to be with respect to the net j, so it is going to be net of net j 1 minus sigmoid of net j. Once again, this sigmoid of net j is actually oj, therefore 1 minus oj. This is what we are going to get. So ultimately, we have actually determined that second part is oj 1 minus oj. The first part is this. So you can combine both two things into this plugin, both these two things into this particular formula. So what you get? You get minus of Tj minus Oj multiplied by Oj 1 minus Oj. This is what the formula is. So here, what is the target and what is the output given by your thing is actually going to be given into this particular scenario. This particular quantity, we have seen that we have obtained this particular quantity, and here I'm going to put a small thing to you that I am going to call this thing as a sigma I, sigma j. I'm going to call it sigma j. This term I'm going to call as sigma j. So if you know this thing, means you actually know this particular thing, and now you can update your things, update your weight. How can you update your weight? You have to update weight using minus of eta times some constant time, this particular quantity multiplied by xj. So this is settled down. That for the output thing, this is what the formula is. Any problem in this? Eta time, this particular part multiplied by xj. Make sense? So that's why this was written into that particular part. Any problem? Yes or no? No problem? No problem? Great. Let us see that second part. This second part of this proof actually that try to find out the value of these parameter for this particular setting, where means you are into the when you are inside the hidden unit. Okay, when you are inside the hidden unit and you want to find out ed upon net j, so you know that any unit has multiple outputs. So for all those outputs, you have to find out the summation. You actually find out this particular quantity for all the things which are there into your downstream. Downstream means, once again, if you pick any of the neuron, you see that to whom it is going to be connected. This is what the downstream of j is. Okay, so this particular formulation that you usually say, because on here again there is a problem, as into the same way that it's not going to be dependent on the same thing. So you can take it towards the output layer and you say that it is a del upon ed upon net del of net k, and then you say that del upon net k divided by del upon net j. You can apply the chain rule once again. Any problem in this? This is the same thing that you are going to apply the chain rule. If you apply the same thing, then this particular quantity comes, that is with respect to the output layer. This particular quantity is with respect to the output layer, ed upon net k, the same kind of equation that is here with respect to the output layer. And for this we have seen what? We have seen what? This is the answer, that this particular quantity was this is negative of sigma j, negative of sigma j. So I can put the negative of sigma j here since it is k, I can say that's of minus negative of sigma k. This part is clear. I have just taken from the previous, because now if you are into computing something and you are actually finding out the same thing into the output layer, for that we have actually solved earlier. So we can use the formulation from there itself. Now let me go once. Now let me explore this particular quantity. Again, I can apply the chain rule once again. I can say that net k upon oj and oj upon net j. This particular quantity is a very important quantity. Net k. What is net k? Net k is equal to wk1 xk1 plus wk2 xk2 dot wkj xkj plus dot whatever the number of connections are there. What is oj? Output of the jth unit. Output of the jth unit. Output of the jth unit. And you are talking about with respect to the next layer. Look, we are going to find out the parameter here, but oj is output of the jth unit. Okay, oj is the output of jth unit, and it is going to be fed somewhere. So it becomes input now. It is xj. It is the xj, because it is going to for this unit it is going to be x. Makes sense or not? Does it make sense? So only this term is going to survive. All these terms are again going to be cancelled. And because of this, and since this particular quantity oj is equal to x, so this time this is going to vanish. When you are going to do the differentiation, this is going to be cancelled and it becomes 1. So what remains is w kj. So it here you get this particular quantity as w kj. Okay. oj upon net j, again the same kind of equation, that it is a this is a sigmoid one, sigmoid of net j. Again, for this you know the derivative oj 1 minus oj. Now we got this particular equation, and this particular equation we can we can we can put like into this particular way, that this particular part, because there is a summation, and this summation does not involve this particular j part, so you can take it out, because for all these things it is going to be same. So oj 1 minus oj multiplied by delta k and w kj. So this is what the equation is. So the value of this particular quantity, because there was a negative has been actually in this particular equation, it has been actually done small modification, that I have taken minus at this particular quantity, and by this we can compute this particular quantity. I call it again delta j, delta with respect to the hidden layers. Again, we can utilize a similar formulation to find out that what we need to update. Here negative sign is not there because I have already taken care of that particular signature, and therefore this particular formula comes into the picture. The complete formula is this, the same thing we have seen earlier, that if the output units are there, if you are updating the weights with respect to the output unit, then you are going to use delta this formula. Otherwise you are going to use for this longer formula when it is a hidden unit. All other things are actually same. They doesn't have any kind of effect, that you actually try to see that how much you have to update, and you keep updating for all the data items which are actually there. So this particular complete algorithm is called what? Backpropagation. Using this kind of formulation, you can now train the things end to end. Once again, if in multiple layers are there, at the final layer you can utilize this formula because it is with respect to the output layer. But when you want to find out this particular thing for the hidden units, you need the outputs. Output means the values which are actually present over here. Using these values, you can find out the value into the first hidden layer. On the same way, if you want to find out the value into this particular layer, so they would need what is inside the output, which you have few minutes back compute into the previous step. So these values are already available. So use these values to find out the values over here, and go ahead into the same way to find out the values into all the hidden layers. This is not a new graph for us. Multiple times we have seen that. Last landscape is not that easy, and I don't know where you are going to start because of your initial conditions that actually you started with. Your initial condition may be something where, for example, this is the error. So if this is the error, you can come here, next step, then in next step you can come here, then next step you can come here, and you may be stuck somewhere here. I'm not sure about this. You may be stuck over here if there is a small valley at this particular portion. If you start somewhere here, you can go down and you can sorry, I don't have very good quality picture because this has been taken from the paper itself. Very interesting paper. If you get the time, you must read this particular paper. Very recent paper, 2018 paper, and they try to visualize this particular surface, last surface. So if your weights are such that you start at this particular location, for example, you start this particular location, you would be stuck into this particular well. So again, this is a big problem. So that's why sometimes people say that instead of only one time running, you run this neural network circuit multiple number of times. Sometimes you will initializing here, you can reach here. Sometimes you initialize here, you can reach the minima. So out of different executions, you actually report that what is the minimum one. This is the best that you can do. However, sometimes it has been seen that most probably if you start, just see this. Let's assume that you start here. Okay. So first step you would be moving this much. Next step you are going to move this much. Next step you are going to move this much. You know that every time the gradient is going to reduce. So it may be a good idea that when you are going to update at this particular point, you compute that how much you have to update. For example, you have to update delta W at the delta w. Okay, let's assume that you have to update delta w at the time t. So maybe at the previous time, if you have updated, may have updated data t minus 1. This much you have updated your weight. So there is a proposal that says that why don't you use this value also? Means maybe some alpha time this particular value plus this value you are going to use this to update the weights. Maybe you can be better. So this particular strategy is called momentum, and it says that whenever you are going to find out do the change, what you do, that you compute that how much change you have to do because of your current scenario, but you also pick that what change you have done into the last time, and use this particular value, some alpha time, that particular value, to actually find out that how much you have to modify. And many other times this actually works, and helps to escape the very sometime very very small kind of hurdles that you have. So if there are big hurdles, so definitely you would be trapped, but small hurdles sometimes you can pass and you can go to the better optimized solutions. This is nothing more than this, that if you want to, if you can apply the same thing to find out the previous one, and because it needs a downstream thing, so if you want to find out the parameter over here, so you use the previous one and you can find out this thing, same thing. Backpropagation guarantees to converge towards the some local minima. It guarantees that it would give you something local minima, but global minima it is not going to guarantee, that we have just seen few minutes back. Okay. No methods are known to predict which with certainty when the local minima is going to cause the difficulty. There nobody initially can. There is no good method that can tell that if you start, for example, with these kind of weights, then you would be stuck. So there is no other way. Instead, just do the multiple number of experiments to find out that what is the best way, what is the best optimization that you can achieve using this particular formulation. As we have talked about, you can use the momentum, multiple networks, etc. Means some other network you apply and find out that what are the initial starting weight, then you can use them to find out the better weights. However, we would come back this thing once again, that there are some other specialized method that actually can increase all these things at later point of time, but initially into the general setting all these things are not available. And we have seen earlier also that it is any Boolean function you can approximate to very nearly, and therefore bounded continuous functions can be approximated very nearly, and 2 layers are sufficient. All these things we have seen earlier. So the backpropagation actually make it possible to train the deeper neural networks, and that's a very interesting idea. Okay. So if a network is given to you, we have few minutes back seen that it may actually get stuck into the local minima. So what happens that initially when you start training, so your training error is going to reduce with a fast pace, but after that the amount of reduction actually becomes small. So generally this kind of curve we are going to see when you are going to train with the number of iterations, the error is going to reduce in this particular using this kind of behavior. if you if you see what is the testing error into the same kind of setting, you would see that initially your testing error would also small. So if this is the training error, definitely you expect that testing error would be higher. This is the generally we think, and this would be higher, but after some time what happens now, this is going to increase. Even if the training error is going to reduce, this is actually going to increase. Why? Something called very strange. What is called that? What is that called? Overfitting. It is happening because of the overfitting. So you can avoid the overfitting using the idea that we have talked earlier, that if you try to see that what is the gradient at this particular moment, you say that looks like the gradient is something like into this thing, and here the gradient is very small. So if you plot these two lines, you can see that there is a point where looks like that they are going to interact. So you can stop training after this particular point. Okay, this is called the early stopping, very important criteria, and sometimes this particular thing is known as the elbow method. Okay, you can use the elbow method to do the to develop a stopping criteria. Make sense? Yeah. So there is a coding example, and it is available on this particular website. And similar thing you have also done into the previous lab that was onto the neural networks. So you can just go and see this particular website. Here, what the things is that this is the data. Okay, if you can see this data, so there are some positive red and green points. So they are actually they are interlinked. So this is the red point, this is the green point. So if you try to develop a kind of classifier, so classifier would come up even if it comes like this, that below things are actually green, above things are red, then also there is a problem, because you can see that these points there is no good classification for them, so system would have the error. So multiple thing you can try. For example, if you apply the logistic regression is again the try to find out the single fit line. So this kind of line it is going to give you on the on in logistic regression, it is going to give this particular line. Above things are red, below things are bad. So you can see that this line is not going to be very good, because these points have the wrong kind of classification. So this particular blog actually suggests that I am going to deploy this kind of neural network architecture. Okay, so how many layers are there? Two layers. One is this, another is this. This is hidden layer 1, and this is the output layer. Here are the parameter and here are the parameter. How many hidden layers are there? Single hidden layer. Okay, and how many neurons are there into the hidden layer? Okay, I'm good. Let me tell you that how many neurons are there. How many input layers? How into the input layer? How many input would be there? Two, because it's a two-dimensional data. Okay, output two classes. So I'm going to put two neurons at this particular place. All right, so let me start training by having only single neuron into the hidden layer. If I train using single neuron at this particular place, I get this one. I get this kind of line. Okay, single line. Okay, this is the what I'm going to converse. Again, it is the same thing as we have seen as a logistic regression. If two neurons you put, it is going to be better, and it looks like something like this. It is going to be better, and it looks like something like this. Okay, makes sense. If you put three, then this kind of structure you are going to see as a decision boundary. If you put four, it becomes even better, but I think the three was sufficient. Okay, if you put five, it gives you some this kind of thing. Okay, if you give 20, it gives you this. So all these things are actually overfitting. So the it looks like that you are best when three things are there. Only three hidden layers are actually kept at this particular place. Three hidden neurons are sufficient into the hidden layer. This is what the code is. I would not go into that much detail. You can just copy paste and just execute that code, and everything you can see the result. Make sense? Thank you very much.